Swayam Prabha. Digital India. Educated India.
This topic is very much creating an interface between the engineer and the geologist. Because when we are talking about the rock mass, and we have defined in our earlier classes that rock mass is something which incorporates the intact rock as well as the discontinuities. And as a engineering discipline, maybe in for the mining engineering or for the civil engineering, we are very much interested to use this rock mass as a material for the construction of the different types of structure. Maybe we are using that rock mass to make a structure, or we can make a structure within the rock mass, or we can make a structure on top of this rock mass. So we can have the three different ways of use of this rock mass is concerned. For any real life projects, this rock mass is used in a various ways. So the idea came long back, and the people thought that because in earlier days, all our design was based on the uh, our own experience, the experience we are gaining over the period of time, and based on that, the people were not able to pass the knowledge from one generation to the another generation. So later on, the people feel why not we have to have a some number system so that they whatever we are gaining out of our experience, we can find some mathematical numbers. And once we are getting these mathematical numbers or some digits, that will be that will be a that will be a mode of communication between the two persons sitting at far away from each other, right? Say for example, in our classes also we have a grading system, and we are calling a excellent uh, to up to D grade, to C grade, B grade, to A grade. So based on if I'm communicating this to my to one of the researcher at in other countries or far away, that my student have got EX, so immediately he will understand that the type of student he is or she is. Okay, so as soon as I'm talking about the grade of a student, the other person will immediately recognize that okay, the student, the category of the student, or the academically how strong he is, based on the grade we are giving into the class in the classes, more or less, right? Most of the time, the chances are that the student will be very good if he is scoring EX on most of the occasions, right? Or maybe if he is getting grade C, so we can say that okay, he is okay. So we will try to see what are the other areas he is doing excelling well. Maybe in extracurricular activities he is spending time, and maybe he is good in that activities also. So so prime motive of this classification is related to generate a communication system between two people, and these two peoples can be a researcher of the same in the same field, or maybe a researcher or some geologist, a geologist and a design engineer. So if a person from a mine is communicating to me that this underground mine having a good quality of rock, or maybe a very excellent quality of rock, then I can easily conceptualize that what will be the strength will be, what will be the strength of that rock is more or less, and what type of support is needed. We will discuss about the support in coming classes. What type of support is needed for such type of structure? If the size of the opening will be of a particular maybe a 4 meter diameter, or maybe 5 meter diameter. So what will be the size of, in that size, what will be the support requirement? So without going into much detail about the description of the rock mass, a design engineer or maybe a geologist can understand very well that what type of treatment is needed for this type of rock masses. Right? So rock mass, as we have discussed, that rock having intact rock as well as the discontinuities. Right? So I will show you some of the photographs, and you will recognize that how it will be difficult for a rock engineer to get some idea about the rock mass when we will look into this, how it is going to behave, because not only the rock mass, but the size of your excavation or the type of your excavation, type of the opening we are going to make into such type of rock mass is also going to affect the behavior of those structures. So not only we have to look into the property of the intact rock, not only about the property of the discontinuities, but also we have to look about the type of a structure we are making into. What will be the direction of those structures with respect, which will find it out, right? So this is very very important topic, and this will be something called you will so these knowledge we are gaining over the period of time, maybe 20-30 years of experience of dealing with such type of things. These things came into our, we can conceptualize those type of things, but the people have developed by this classification system, which was started in 1943 by a civil engineer, uh, Terjagi. Carl Terjagi has given the concept. He has first time he has uses this concept for this classification system, and later on, so many systems have been developed, around all over the world. And out of so many developments, we are recognizing few of them, which are very very popular. And this popularity, definitely it will depends upon the easiness of use and the, or maybe the simplicity of the classification system. Okay, so we will see what are the things are there and what motivates us to have the classification like this. Okay, so let us see our first slide. So the first slide is like this. Now you can see the figure. This is red color figure. This is a rock, and you can see it is the discontinuities are such that you can see a brick type of structure. And this photograph was taken by me itself while visiting a iron ore mine, and you can see this is the hematite, and you see it is like a brick shape, right? So these bricks are being formed when we have three sets of discontinuities, and you can see the discontinuities are very very orthogonal to each other, I mean, perpendicular to each other, right? And this is very something different, right? So these discontinuities, we have to see these discontinuities, how it is going to affect the stability of the rock mass. So here you will see it is rock mass is an assemblage of intact rock material separated by geological discontinuity. So here you will see the intact rock is there and there is some discontinuities are there. Okay, and you can see this is open, it is not closed. So this joint is open. So this is a type of this is a joint, and this joint is open. So this is a type of joint which is called the open joint, right? In next figure you will see that the joints are visible, but you cannot find a separation between these two. You can feel that there is some sort of a line is there, which is defining a demarcation between the rock on the left side and the rock on the right side, but you cannot find any separation between that. No, zero separation is there. Okay? So this type of joint, so this is also a joint, right? So this is a joint, but it is a closed joint. So no separation is there at all. Whereas in this figure also, again you will see that similar to that, the failure of this rock pieces is happening to be on a particular orientation, but you can see this joint is much more compact comparison to what we are seeing over here. But other observations are there. There is maybe a presence of some different orientations of joints are there, which are very orthogonal in nature, but those joints are not open at all. So the question is that in rock mass there are uh, divisions or categories are there. One is called not two categories. Maybe we are dividing this rock mass is a uh, is a component or a function. If we can write like a mathematics, so we can write like rock mass is a function of intact rock and geological discoveries, right? So if I want to find out the behavior of the rock mass, I have to have a knowledge of the behavior of the rock, intact rock, as well as I have to get the values how the geological discontinuities are affecting, right? So the understanding of both of them is important. So as I told you in previous classes, that intact rock, how we can categorize this intact rock? Uh, we can categorize this intact rock in a lab or maybe in a field also, but there should not be any discontinuities. And how we can categorize? We can find out the different strength properties. Okay, because here we are mostly interested in our strength properties. So we'll try to find out what is the uniaxial compressive strength, or maybe tensile strength, or the shear strength, or maybe cohesion, friction angle. What are the different strength parameters of this intact rock is that we can find it out. So we can take a piece of this intact rock here. We can prepare the sample as per the ISRM standard, and we can test it, and we can get the different values of UCS, tensile strength, cohesion, friction angle, like that. So we can categorize these rocks based on the intactness is concerned. We are looking at in a mathematical form, and we can categorize it. Similarly, the geological discontinuities, right? And in one of the class, I was talking about the geological discontinuities as well. But how we can classify this geological disorder? If I'm telling that it is a joint, no, it doesn't it is not going to fulfill my purpose. We have to categorize this joint or quantify these joints, no? We have to quantify these joints, like what is the difference between a joint which is there in this figure, figure number 1, top figure, or in the figure on the left side, or the figure on the right side. What is the difference between the geological discontinuities between these three? That you have to find it out. Then only, like say for example, in all the three figures, if I can find the intact rock strength to be same, but the geological discontinuities are different. So how to quantify these geological discontinuities? Okay, then only you can get the clear picture of rock mass. So we have to categorize these geological discontinuities, or maybe quantifying this geological. Quantifying means to develop some numbers through which we can differentiate between these three different types of rock, or maybe the rock with which we are dealing with. Okay, so we will try to see that, and here you can see lab test shows no reflection about extent of this. Okay? So lab test is not doing you, not telling you anything about it. When we are testing a rock into a lab, it is not giving you a effect of discontinuity data, right? So here it is very important to find out what are the different parameters by which we can define these geological discontinuities, right? And that was a active research, and this there are plenty of parameters are there on which we can define these geological discontinuities. And there was a committee formed by ISRM, International Society of Rock Mechanics, in 1974, and they are coming up with 10 different parameters. They come with 10 different parameters which will define the geological discontinuities, and we can have these 10 parameters to quantify this geological discontinuities, right? So what will be the overall what will be the overall effect of all these discontinuities, all these 10 discontinuities? That we have to find out. And you see, this 10 numbers is a big number if you are trying to quantify them. So people try to make this number as less as possible. A general consensus was there. Okay, 10 numbers are good enough to quantify the geological discontinuities. But even though it is posing a lot of uh, uh, posing problems in terms of time, labor, cost, like that. So to cut down these 10 numbers to few numbers, the people have tried to work hard, and based on that, you will see the different classification system was given by the people all over the world, right? Now here you can see several variables, several parameters which is defining this discontinuities. Maybe the orientation of these discontinuities, means what is the direction of these discontinuities, what is the roughness of this discontinuities, that we will see. I think I had also showed you during our in situ strength test the joint roughness, roughness, how rough it is, no? Or maybe it can be a very um, um, flat surface, or maybe, or it can be a very rough surface. Or what is the spacing if there is a opening between these two joints? If it is an open joint, so what is the spacing between these two joints? What is the filling material? So many parameters are there which we are going to discuss later on. Okay. So this is affecting, all these properties are affecting the effect, the response of the rock mass if some force is being applied onto this rock mass. As we have seen during our in situ strength determination, that when we are applying some stresses, uh, what will be the strength? So I had asked you, I had also told you that the with the presence of the discontinuity, the strength of the rock mass will be less comparison to the intact rock strength. The reason is there. No? So how much? What will be the impact if I am testing a sample from this? All these three samples from this rock mass, and the size is very big, incorporating few joint sets. So joints, as we have seen here, what will be the uniaxial compressive strength? Now, if no joints are there in the sample, and if joints are there in the sample, what will be the compressive strength of the rock mass? So this way we can find out the effect of these joints when we are finding this strength of the rock mass. And that's why it is very important in our rock in situ strength determination that we want. If your structure is very important um, uh, for as far as the strategic nature is concerned, or the safety reasons are concerned, we have to have such type of test is required so that we can capture all these variability. No? But there are some ambiguities are also there. So that we will see, because we are again estimating the values of the effect of geological, just estimation. It is not exact values or the exact effects we are capturing, but again it is a estimation of that. So with again some approximation, we are trying to capture the effect of this geological risk. So again, that is a approximation. No, this is not an exact values. So because we are trying to play with the nature, and the nature is very um, unpredictable, and if from those unpredictability we are trying to get some authentic results so that we can use it for our design purposes, or to generate some model into my mind about the rock mass. Okay. Now come to the next slide. Now I can skip this slide because we have already defined the joint, and joint is simply we are defining a break or geological origin in the continuity of a body of rock along which there has been no visible displacement, no displacement. So this definition was given by ISRM in 1974, and they have standardized all those definitions so that there should be a general consensus for the scientists all over the world. Okay, and the people will follow the same definitions, follow the same terminologies as well to define these parameters, right? So that we can communicate freely between these. So we have this joint set we are calling one parameter. We have one of the parameters is defined is called the joint set, and that is defined as a group of parallel joints is called a joint set. And I will show you in one of the photographs. And we can define a joint system when joints are intersecting. When parallel joints are there, they are not going to cross each other, right? If parallel joints are there, they are not going to cross each other. But if it is non-parallel, definitely they are going to cross each other, right? So those type of joint is called the joint system. And then there will be a two joints will be there. One is open joint and the filled joint, right? And another parameter we are defined the joint frequency, because the separation between the joint will not be uniform, no? Because it is varying. So we are trying to find it out how many joints are there per unit in 1 meter length. How many joints we have observed, because gap points is now based on this ISRM, we have this 10 parameters are there, which we'll see slowly and slowly, and what are their effects are there. One is called the orientation, and this is defined by the two parameters, that is called dip and the dip direction. I expect that you have already gone through these terms, dip and dip direction, in your geology classes. Okay, and with we can measure this dip and dip direction with the magnetic compass and the clinometers, right? We can find these directions with respect to the magnetic north, right? So our coordinate system will be now in case of we are finding all these parameters. That is called a term we are calling it as a geological survey. So when we are going for the measurement of all these 10 parameters in a mine or a field, we are calling it a geological survey. And during this geological survey, we are trying to determine all these parameters. So whenever we are visiting such type of fields, we can determine the dip and dip direction or any joints. Okay, so what is this dip and what is this dip direction, which will define those who have not known to this terminology. Again, we will cover it with some pictorial representation over here. Okay. And then we have this spacing, persistence, roughness, wall strength, aperture, filling, seepage, number of joint sets, and block size and shape. Okay, so all these 10 are defining the discontinuous. If I'm defining these all these 10 parameters, these are the major parameters which is defining the geological discontinuities. So other parameters we have just left aside. We are not considering those. This 10 is good enough, and these are the major parameters which define these geological discontinuities. Okay, and we are trying to find out what are these parameters and how we can measure it. Right? Say for example, spacing. So the definition is very clear cut, so that there should not be any ambiguity between two people, right? Two people who is measuring this parameter. And that's why this clear cut definition is very important for us to follow, so that there should not be a contradictions between our approach for solving this problem. And then we can say that okay, our communication. I had told you that communication between the two people. Communication between the geologist to geologist, communication between the engineers to engineers, or the communication between the geologist to engineers, or maybe a technical person is or a technical person is talking to a administrators, no? Those who are not knowing anything about this orientation and spacing. But you can see that what is the difference between by some numbers, that okay, this number is 10, this number is 5, and this number is 2. So anybody can understand that okay, the difference between these three is something twice of the first one, second one, or maybe twice of this one. So you can get such type of ideas, so that you can communicate between your with your with your management, with your geologist, with your design engineers, like that. So we'll see. We will go through all these parameters by some pictorial representation, which is there in our next slide. Okay. Okay. So there was assignment, because this is the so this I can give you some time. Okay. Now, if you can see, now you can see some of the activities is being carried out uh, uh, by by us in a mine, where we are trying to quantify the geological discontinuities. Now you can see everything is. Uh, uh, I'm here. Dr. Rakesh is here, and these are two PhD scholars we have, and we had worked maybe 5 years back with one of the company. And you see, we are trying to find out the because these two people are stretching a what is called the tape. Okay, I'm having a length of about maybe 10 to 15 meters. Okay, so they have gone up to a maximum length of the tape, and we are trying to find out the frequency, number of joint sets in this particular length. How many joint sets are there? So you can see in actual situation, the things are very different, right? You are not able to find out what are the joints are there and what are the joints, because if I'm talking about the joint is the geological discontinuities. No, it is from the nature itself. And here, if you can see, this can be a mechanical in nature also, because we can break this rock by drilling operation. You can see some holes, sign of holes are there. So possibly some blasting has taken place, and because of that, the rock mass is having fragmented. So we have uh, to see whether is there any sign of discontinuities. So everything is not. We cannot consider this mechanical break as a joint. This is very important for us to understand. Consider this mechanical break as a joint. So whatever the natural joints we have to consider. So we are trying to find out the geological, the number of joints in a per unit length. So that is one of the parameter, and that is important to find out the various things also, right? Here again, you can find we have taken one long this one tape, and we are trying to find out identifying the joints, what are the different joints that there, and we will measure the various parameters, whatever the various parameters is defined you. So that is being measured in this process. Now here in this case, we are trying to find out the strength, wall strength. One of the parameter was joint wall strength. So here I have identified, we have identified that this is maybe a joint which is somewhere extending along this direction. So the strength of this wall is trying to be measured by one of the handheld instrument. One of the handheld instrument, that is called the Smith hammer. Okay, so uh, you will get an opportunity to see this instrument in our lab. So with this, we can find out the strength of the rock, the wall joint wall strength. We can find the strength of the rock wall. Okay. So, and we have some tables like this, and we are trying fill this table, where you can see what type of uh, structures are there, whether it is a joint or what type of roughness it is, like that. So various terminologies we are trying to scan or measure during this type of process. I will not go into much of that because it is unnecessary. It will create. Uh, it is not required at this preliminary stage of. Okay, so I will just go through some of the other. Okay. Now, in one of the figure, you will see that. So orientation. So orientation, we are trying to find out the direction of the joint with respect to the magnetic north, and how and so this is what we are trying to find out the dip direction, and dip we are trying to find out the inclination of the joint with respect to the horizontal direction. So with the horizontal, how much it is dipping below, so that angle we are measuring. Spacing is the perpendicular distance between the two adjacent discontinuities. So we'll go to the this one. So here you can easily find if two joints are there, what is the distance, perpendicular distance between these 2 points, right? With between these two discontinuities. So that is going to give you the spacing of discontinuities, right? Similarly, we are trying to find out the persistence. This is very, very important. The persistent, the extent of discontinuity within the rock mass, because like in this case, if any joints are open to us, say for example this joint is being shown over here, it is being continuing from top to bottom. So what is the extent in z direction, which is not visible to us, which is being covered by the rock mass itself in the third dimension. So the third dimension is not visible to us. So we have to identify up to what extent it goes. It goes to 1 meter, 2 meter, 10 meter, or a kilometer. So that extent we have to know about this joints. What will be the extent of this discontinuity within this rock mass? So that is defined as a persistence, right? Similarly, we are talking about the roughness. Na? So roughness, we are calling it a surface undulations, na? Surface undulations or waviness. And one scientist is there that is known as Barton. He has defined a term called joint roughness coefficient. Okay, so now if you can see this photograph, you can see that he has defined a joint roughness coefficient. So he has defined a number from 0 to 20. He has defined a number called 0 to 20, that is called JRC. And this number is being assigned to types of roughness which has been shown over here. The type of roughness, he has done a lot of field experiments, a lot of field investigation, and with his own experience, he has quantified or the categorized 9 different types of roughness he has defined, right? So 9 different types of roughness is defined, and for each roughness, he has defined some numbers, right? Say for example, if the roughness is very rough, so this number is about 80 to 20. If it is very plain type of joint, so its roughness number will be 0 to 2, like that. So he has defined a scale of this roughness through which you can very much, by looking at the roughness of the rock which has been provided to you, and by looking at this figure, you can identify the roughness of your discontinuity. But one problem is that here we are talking about the 2D surface, right? Here we are talking about the 2D surface, and we are assuming that in 3 dimension, the extent of this discontinuity is same. The extent of this discontinuity will continue in the same way as it is shown in one of the line, but possibly this is not happening, right? So we are trying to say that this line is representing, if I'm talking about a 3 dimensional structure, a 3D surface in which we are talking about the roughness. So this line is representing the representative, which will tell about the maximum roughness which will be provided right at the surface, right? So it is representative of all the possible lines which can be drawn on the surfaces, right? And also I had showed you one of the photograph that this roughness, like this effect of this roughness will be a directional property, right? This effect of the roughness, so we will discuss later on also. Or also I will show you that photograph that I had shared you during our strength test, and it will be more realistic if you will compare those photographs with the rock mass knowledge, no? So it will, you will see that the effect of this one rock mass will depends upon the direction also, huh? Like if the roughness is being defined like this, and the two surfaces are there, upper surface and the lower surface, and if I'm trying to slide in this direction from left to right, so the resistance will be something else. And if I am trying to push from right to left, the resistance will be something else. So there will be a difference. But if it is a very plain surface or the smooth surface, either direction, it will be same. It doesn't matter in which direction you are trying to slide it, no? But if I am if you are going for a very micro level of study, again you will find some sort of a difference, huh? Even if it is a planar, but you will find that the movement from left to right and right to left, there will be a difference, but this difference will be very, very minute. And that maybe depends upon the orientation or maybe heterogeneity of the material, huh? It will depends upon the heterogeneity, so that variations will be very, very less. But this roughness is affecting a lot. If I'm pushing the rock from left to right and the right to left, so as the roughness is going to be more and more, this effects will also increase. So that's why, yeah, this roughness is very, very important property, and we will see how. Now, this photograph, if you'll see, like I am trying to show you a three-dimensional cuboid, and if you'll see, if I'm looking from this side where it is little persistent, if I'm looking from right hand side of this cube, so and only these three lines will be visible to you. So you cannot see how much it is going into the three dimensions. So you do not know. So in this case, you will find that a particular joint, which is shown over here. If I will see this, so I am interested to find out up to what extent it is going into the rock mass. So that is defining the persistency of the joint. No? So if it is more and more, it means that it will destabilize the rock mass to a larger extent. And if the discontinuity is not persistent, and we can define it as a non-persistent, so here you can see there is a break at each occasion. So it is not a persistent type of joint which continue from a longer depth, a larger depth. So this is also very, very interesting. And you can see the dip direction we have defined. We are putting the magnetic compass, and we can measure the orientation of this particular line. We can measure the direction of maybe we can measure the direction of this line, or maybe we can measure the direction which is showing you the largest dip. And how we can define the largest dip? By some practical experiment. If you can pour some water on the inclined surface, maybe some inclined surfaces are there in your in some places. So if you can put some water over here, the direction in which the water will flow, that will show you the direction of your. So that is the direction of maximum dip. No? So this is what we are trying to measure, the dip. This we can measure with the clinometer, and this clinometer is also coming along with the magnetic compass. So sometimes the magnetic compass is separate, clinometer we have to have separate instrument, otherwise both of them are coming together. So a geologist or a engineer will be very, very helpful to carry only one instrument to measure these two parameters. So we can measure this direction of this line. We can find out what is the direction of this line. So there are two direction. One is your dip direction, another is which is along this plane. So this is what the plane is. So that is called the strike directions. Either we can measure the direction of the strike, and always this, if we can measure the direction of the strike, the direction of the dip is 90 degree with this strike direction. So we can measure either of them. Either we can measure the direction of the dip, or we can measure the direction of a strike and convert it into a dip direction. Okay. And with the help of this clinometer, we can get these values of beta. Okay. So that is going to give you the maximum leak, right? So there is called the dip and the dip direction. We can also define the apparent dip, which is out of the maximum dip. So if I am measuring a dip, so in some other orientation, that will be called the apparent dip. So I will tell you about these things in through some assignments also, so that you will be able to understand this basic terminology, and you can correlate with your geology classes with what we are studying in ERM. So whatever you are studying in geology, that is supplementing the knowledge what you are going to gain from this ERM or subsequent classes in your core discipline. So that is going to be helpful. So I will try to give you some assignments so that you can interconnect between what you have gained from geology and whatever you are studying from here, how you can interlink with each other, so that you can find it fruitful, that it is not it is going to be very very useful in your future careers, as well as to understand the various subjects which will be followed in the coming semester, not only with this semester itself, but from the coming semesters also, those knowledge will be useful for you. And once you are going to interact with those people, maybe a geologist, or once you are going to do some projects, or once you are visiting some of the mines like this, you will be aware about all these terminologies, no? So you can easily understand what these geologists are talking about. Like you are visiting a doctor, and you have no knowledge about the medicines and the diseases at all, so you will be just a mute spectator, no? So we have to have, as a engineer, as a geologist, we have to have this to be a this is so this linkage we have to establish now. Now here in this figure, this is being tried to show you that how these joint sets we are defining. Now here you can see in this particular plane, this is square area, and it is being represented by a tape. The tape we have shown you in the field. So here you can see that there are these dotted lines are there. One set is defined by this dotted line, which are parallel to each other, right? There are another sets are there which is inclined. Big dotted lines are there, and there is another form lines are there which is oriented in this right this way. So there are three different lines are there which are interacting with each other. So these three lines are interacting with each other, and they are not orthogonal at all. So you will see that for this particular joint, the vertical one, if I can measure with this tape, we can find out this the distance between the two subsequent joints. So if there are more than two or three joints are parallel to each other, so that is called the joint sets. So in this figure, you will see that but there are clear-cut three joint sets have been created. There are three clear-cut joint sets have been created. One is the vertical one, and two are the inclined one, right? So we can find out the spacing between the joint sets. So for each joint sets, there will be a spacing, right? So for this example, we can find out the spacing between the joint sets. For the others also, we will find, like here it is defined by some B2. Here it is defined by S3. Here it is defined by S1, right? So must be we are defining all these joint sets. So what is happening here, I am trying to measure this joint in a horizontal direction, and I'm establishing a relationship between this between the different spacing of the joints, right, with some trigonometrical relationships, and we can find it out, right? And if I can find out, like some of the cases we are lucky that all the joint sets are very parallel to each other. Some of the cases it will not be. So in those cases, we are trying to find out the average uh, spacing. Average spacing. That is the concept we are using. We are trying to find out the average spacing of the joints. And if you can have, and based on that average spacing, if you can have a spacing of all these three discontinuities, S1, S2, and S3, and the average value is there, we can conceptualize that. If we are trying to conceptualize this arbitrary oriented joints into a simple block shape, by assuming that the cuboid is getting formed with this average set discontinuities, having all the sides are S1, S2, and S3, and this is forming a block of size, this one, and the volume will be S1 into S2 into S3. So we are we are means simplifying our model. While if somebody is looking at the figure as was shown in this field, we are trying to make it a geological model of having a small cuboids, if it is forming a cubes. Okay, so we are trying to find out the average spacing, and with this average spacing we are trying to find out the block size, right? So this block size will be useful for us to define, and as we have seen that this block size is defined. So this was one of the parameter here. So we can define the size of the block. And what will be the shape? No, shape, how we can define? We can find out the shape. If it is a orthogonal joint sets are there, so it is not going to form a cuboid, but maybe some tetrahedron or something, some other shapes will be going to form out of this. Maybe seat structures will be formed. So we can determine what will be the block size and what will be the shape. How we are finding this shape we can get it from the orientation or the deep angle of the joints, right? So here you can see that out of so many parameters, I have tried to explain you orientation, spacing, persistence, roughness, wall strength, and aperture. This aperture is the spacing between the two surfaces of the joint. No? So that is called the aperture, right? If it is a closed joint, so your aperture is 0. If it is an open joint, some aperture will be there. So we can measure this by simple scale, or maybe the slide caliper we can use if you are trying to be very accurate. So that scale is good enough. So we can use this caliper to measure this aperture. Next thing is the filling. Filling is important. We are trying to find out what are the material. If it is a open joint, so sometimes we can find out some fillings are there, some loose or the gauze materials, waste materials are deposited between these joint surfaces. So the filling is important. Sometimes what happens, this filling material is very hard, and it will bind these two surfaces of the joint together, and it is not acting like a joint at all. It is not acting like it, because this is now pasted together, and it becomes so strong that the chances of failure will be very less. And sometimes this filling is so weak that it will accelerate your movement. No? Say maybe some sort of a clay type of material may be deposited there, and if the water is present, so it can slide. No? It will slide, and it will be a cohesionless material. So no bonding will be generated between the joints, between the filling materials. And if the filling is some of certain thickness, it is nullifying the effect of your roughness at all, completely. Whatever the roughness is there, if it is roughness is very high, and if the filling material is of very clay in nature and the water is there, so it is not so the effect of roughness will be zero at that point of time. So some of the things, what I want to say that if one parameter is increasing the strength of the joint, sometimes the same parameter in a different way, it can decrease the strength also, right? So we have to see how these things are enhancing or reducing their strength. So that's why we have to see in actual situation how these two are interlinked with each other. So interlinking of all these parameters are important. Then only we can develop some mathematics to find out mathematics which will be interrelated with each other. Right? And the last which I had not discussed is that is called the seepage. Seepage is related with the water. How much water is present into the that area, because the water is always playing a negative role as far as the strength of the joints are concerned. So we have to find out if it is a dry rock is there, no water is there, the strength will be maximum. And if there is a presence of water, it is going to reduce the strength of the rock mass also. So we have to find out the possibility of this rock, this water in that, and if the quantity of water is more or more, it is going to degrade the quality of the rock mass as well, or the response of the rock mass under such type of stresses. So we have quantified all these things. So these are the 10 points which we are going to which we can
The
we have
slides are not very.
which we are. So these are the parameters which we are going to see. So these are the 10 parameters we have come across in today's class. And I will encourage you to read more on these topics and try to conceptualize it and get more into that so that we can discuss more and I can get across questions from all of you. And maybe we can generate our understanding by solving some of the assignment problems, and that will be very very interesting for you to solve, right? So I think this is all for today.